So welcome to the seminar series in the Gemini Center on Quantum Computing. Today we have Hsuan-Yin, who is a research scientist at Simula UIB. He will be talking about quantum error correction from a classical friendly worldview. So please take it from here, Hsuan-Yin.
Okay, thank you for your introduction. And thanks for the invitation. Yeah, so today I will try to, using this opportunity to join with the Gemini Center on Quantum Computing and also our Friday seminar to give you some very basic tutorial about quantum error correction. So I think most times people, when they hear about quantum or quantum computing or quantum information, they will get afraid because they don't want to deal with the hard math. So I will try here in this talk, just try to want to let you see, okay, if even we just know the classical word or the classical math, it's still able to understand and to solve problems in quantum error correction. But of course, there's still something not happening in classical world, and I will explain and how to a small test to see how exactly quantum world would behave in this kind of scenario. So yeah, I will try to make it very classical friendly, but of course, if you see any questions or any problem, just ask me. Okay, I need to move to here. Yeah, so I mean, why these days quantum error correction or error correction in general is very important for quantum device? Because the nature of the quantum bits are very unstable. So people need to describe this quantum bit by statistically or probability. So this is by nature, the qubits are very unstable. So people propose error correction to make more control to protect this qubit to make it more stable. And on the other hand, if you care about the cryptography and the Peter shows that it's quantum factorial algorithm, if you have a quantum computer, then you can break the security or the public key systems in the modern days. But actually it's a bit broke because they need this 10 to 3 power to 3 and 10 to power 4 qubits to implement. And the operation is also very big for this quantum factorial algorithm. So if you have heard some recent news that IBM maybe do hundreds qubits, but this is still far away from this kind of approach. So even you want to break this cryptographic security now, it still will not happen. That's my observation now. So, but anyway, so we can conclude that, so we at least need to tolerate up 10 to the minus 10 error rate for implement these 10 to the power operations. Because otherwise just go to something errors, which is also you cannot get correct message. So the modern state is in general, I mean, of course, these numbers actually keep updating in these days if you have keep track on the quantum magazine stuff. But in general, it's just 10 to the power minus 2 and 10 to the minus 3. So again, this is far away we can do. So, but to me, for research, to me, for information theory and coding, I mean, to me, why it's actually for us to do this, right? So I think it's like a father of quantum computing, Preskill. But anyway, he predicts that, I mean, in at least 20 years or 30 years, I mean, you will not avoid the quantum noise, the qubit noise in this time. So no matter how quantum device you design, you will always make the noise. And if we want to implement some quantum circuit in practice in hardware time, then you will need, of course, I mean, you will encounter 50 to 100 noise qubits. So this is for sure. So this is actually quite small number. I mean, compare the telecommunications in classical. But to me, I think it's the right time to do that, because if you have observe the classical information theory, actually in these times, I think it's, 3 decades, 30 years. So people actually also work on this very practical problem. It's okay, they call this called finite length information theory. So they just care about small number of bits and how much information or message you can transmit. And then, so that also how the coding can do with this small number of bits. What's the best and what's the fundamental things. And these things actually also not just happen in the classical world. So in the quantum world, there's also people study finite length quantum information theory. So the benefit for us now is that actually we can use all these tools developed in 30 years, such that we can make sure, okay, what's the best we can do, even we have a 50 to 100 noise qubits. So this is at least my motivation to do this research starting from now. So just talk about very general how quantum coding theory actually is used in I mean this year or last year. So of course you all know this supremacy keyword, but in recently there's some researchers, you can see this magazine. So they show that okay, if you design a very good quantum code, which is stabilizer code, I will talk in this talk, that you can actually make 10 times more efficient than what they currently have. So coding actually helps a lot in building up these efficient quantum computings. And these are also, I mean, technical names, but just to let you know, the modern good quantum code, some surface code or color code, bicycle, these fancy name, and also even the most popular codes in this year, I would say, is quantum LDPC codes. They are all actually quantum stabilizer codes. So in this talk, I just want to give you a tutorial and how actually what is quantum stabilizer codes, such that actually we can understand, okay, why this can do. So just a brief story. So the 10 times more efficient is that, okay, people find quantum LDPC codes, which is very efficient in classical, the LDPC code in classical. It's better, much better than, or 10 times more better than this code, surface code. So suffix code was the previous popular code, but now it's beaten by, I mean, but of course, these are just simulation. It's not talking about hardware stuff still. So this is just a prediction, but still, if you talk about hardware, the circuits, there are still a lot of things to discuss. So recently, why it's so popular? Because there's a famous computer science conference talk, 2022. So they actually have 2 papers got award, and they all talk about quantum LDPC codes, and they show that the minimum distance of such code grows linearly in the qubits, which is they believe is good code, because in classical, I think LDPC code can even do almost better than linear. Yeah, so they want to show some similar property in quantum version. But this actually is an open problem. I think it's 20 or 30 years also. But I will talk later once I start to explain the code. So maybe you will know why it's actually so hard to find such good codes with the linear minimum distance. So okay, so this is my motivational story. So let's just go to a bit boring part. So I mean, it still cannot avoid, if you want to know quantum, you still need some math. But the most math you need actually just, not just, but linear algebra. In classical, you also need this. And then the most, I think, the knowledge you need more is actually they call matrix analysis. So matrix analysis is much more different from what we know in the classical world. So I will just introduce the notation first. So this is a complex number, and this is the imaginary unit. And what we call, or how we present a qubit is just, we just use this notation. They call this Dirac notation, bra and cat. And they denote this like, so 1, 0, and 0, 1, you can think about like two bases of the complex field, and the alpha, beta, just some coefficients. So everything so far is good, right? Just classical actually. And also we have a classical tensor product, right? So we can do tensor product of all the qubits, and then you can still get classical discretion. So now go to the point. So what do we mean a quantum code? So we want to define a code over the space of this space, and such that this code has n, capital N. You can think, we call it n-dimensional, but you can think about there's a capital N, the linearly independent vectors in this field. So these are just, you can think about just linear algebra. So I just use the other notation because that will be used later. So in the matrix world, so matrix analysis world, you need to also define something called commutator. So which means that you need to specify this AB minus AB. Yeah, sorry, I think there's a typo. So it should be AB minus BA. And this is as well, so AB plus BA. Yeah, so this is typo, yeah. And for Dirac notation, just to let you know, it's that we use this as a column vector. This is cat, and this is called bra. Bra is just a transpose conjugate. So you can write down the vector like this. Yes. So this is also, yeah, you can write it. It's just the notation wise, maybe you are not so familiar. But if you think everything like a vectors and the matrix, then it's easier. So now it's go to the general part. What do we mean quantum error correction, right? So because we have the basis for the quantum code, right? So n, capital N, linear independent code words or vectors, you can think about this way. But in quantum world, all the operations actually made in the multiplications, and they are made by the operators. They call operators. Actually, it's just a matrix. So it's just a matrix, and operators are working on this. And a code is code detectable. Because in classical we also have this property. So it's code detectable if we pick two orthogonal bases and satisfy this. And again, maybe it's very hard for you to think about why we have this, but we can think about classically. What do we mean in classical? An error is detectable, right? It's actually quite easy. Just if you have a set of code words, but you find an error, and you make this error actually it's not the other code word, then it's detectable because it's not in the set of your code book. So this is the same, right? So you have error, and you try to find the other two code words, and you don't do it. You cannot guarantee it's 0. Then it's undetectable. Yeah. So this is just the classical. Of course, they have a lot of quantum theoretical discussion why this works, but this is a easy way you can look at it from a classical way. And so the minimum distance is also similar to the, if you think about classical, right? The minimum distance is the minimum undetectable errors among all the error operators. So if you think about the classical world, right? You have two code words, and the undetectable error is the distance between these two code words. So they define the minimum of lots of them. Then this is the minimum distance in quantum same as the classical word. It just you need to think about multiplication and then think about addition. Yeah. So, and the least definition is just some number of the matrix and which is non-identity components, and maybe not clear here, but we'll talk more clear later. Yes. So again, in classical, we can describe a code book by the field size or field, right? The finite field, if you are familiar with Galois field, so it's GFQ. So in quantum, actually, we can do similar. So we define something they call Pauli matrix. And you have I, X, Y, Z. And you can think about these are the finite field elements in quantum world. Just these four. And then, so you can think about a way that you think about a space, a complex space in n qubits. It's just a tensor product of these four, right? So you can think about it's a Galois field size 4, and then extend to be n bits. Same idea. But it's not just that actually. So people actually can show that, okay, if you just work on this Pauli matrix, they call this Pauli basis, it must satisfy these two conditions. First is it communicates, and the other is anti-communicates. So this is must be satisfied in these things. And the one thing I didn't specify by the math is because this is a bit complicated about the quotient stuff. So here it's it's called equivalent class. So it's not just all the GN, but just the equivalent class of this Pauli matrix. But I will not talk too much about that. So now we can go to the main topic we have today. It's the code quantum stabilizer code. So it's defined by this. So you want to find a code or vector basis in the complex world. And the list basis is defined by, okay, you pick some matrix. Actually, it's n minus k matrix. And then you times the vectors, it's still back to the vector, which means it's the eigenvalue 1 space. So it's again also linear algebra, eigenspace 1. And then they use this to be as a quantum stabilizer code. And there actually some history reason why they define it. So the most, I think, intuition for me is that why they need to define it, because in quantum world, the most difficulty to do is that you still, because you want to send some information in the quantum world, right? But still, we are living in a classical world. We want to attract this quantum information back to classical. And then we need to do a measurement, like physical measurement, right? So we need to some very, fancy device to measure, okay, what's the state of this information? What's the other state of the other information? So these stabilizers can be thinking about like a measurements. So you have a quantum code exists by you construct, but you do some measurements such that you can explain the mathematical phenomenon. So this is the intuition why this stabilizer code can think of. Yes. And then, of course, based on this definition, people can prove further, which is actually very useful for us for error correction. So for example, this must be Hermitian. And if you know something like algebra, then we also define something called normalizer group. And it just, you pick, because this property, right? Because either it commutes or anti-commutes. And the least group, it just pick up those are commutes. Yeah. So I hope so far it's good. I mean, I think it's so far all still classical. It's just not, we brought up the dimension to 2D, and now it's matrix. Okay. Yes, so remember we have the undetectable definition for the general quantum code, but now we tailor ourselves to just quantum stabilizer code. And how do they define the distance? By using the structures of quantum stabilizer code. So you can prove actually two things. So if you have error operators belong to the stabilizers, and you can satisfy this condition, which is satisfy detectable condition. And if you have some error operators, it satisfy these things, you can also show that this is detectable. So we can show that based on the quantum stabilizer code, the only detectable errors is belong to this set. Either stabilizers or you set minus the normalizers. And so how do we define a minimum distance? We just use the definition before we want to do the undetectable errors, so which is defined by this. So this is they call the minimum distance of error operator of this. And the way to E now is more clear, right? Because the E just if you can decompose like this Pauli matrix, and they just count the number of which is non-identity. So this is how they define the minimum distance of the quantum stabilizer code.
Just a quick word, we have roughly 5 minutes left.
Alright, okay. I think it's then okay, I mean let me try to do more. So yeah, I just try to give you some take-home message, not just about its fancy math. So these are the original structure of a quantum stabilizer code. So these are due by matrix, but we can do that's let me just jump. We can do by classical world by binary things by using something called symplectic codes. This is was proposed by Gottesman, Renz, I think Shor, and I don't remember what's the last S. But anyway, so we can describe such quantum code by just binary vectors, actually. And forget this. So this is the main message I want to say. So forget how quantum matches you do. You just pick length 2 times n binary vectors like this. And this vector satisfy this condition. This is called symplectic inner product. And you need to do some symplectic version inner product, but it's still a complex space within well-defined between inner products. So it's still a linear algebra. It's just the operation you need to change. And then you can find those bases to such satisfy these things. Then you are actually done. So you already find a code in classical world, but still you can tell what happened in the quantum stabilizer code. So this is the main message I want to say. And I did try to get some example. You can see here. And yeah, we don't have too much time. And the other thing I want to say in the abstract is the degenerated. So the one thing I want to emphasize in quantum world, the degeneracy does not occur in the classical world. And it's because of the stabilizer definition. And then it changes the way of decoding of errors. And in such that it would be rewritten like these things. But again, this is just math, but I just want to show you some actually this is related some research I'm doing now. So how actually degeneracy can affect the quantum code we pick is that in classical thing, we would believe, okay, the distance 3 code in the phi 1, this means 5 qubit and 1 dimension, is better than this is just the smaller distance codes. But if you really compute the average error probability by this degeneracy, you will see that actually this code is only good in this very certain range. And this actually happen a lot in why people, it's very hard to find good quantum code because it's hard to design and it's hard to predict. And for most of the time, actually, they just use repetition code, small distance code is still good. So this is the one message I want to share here. So yeah, this is just the final slide. So I mean, our goal now, what we are doing with our PhD and our lab is that we want to develop a good quantum code, but for finite resource. And the finite resource just means that very short quantum code, which is hundreds of qubits, even smaller, or thousands of qubits. Yeah, then I finish my talk today. Thanks.
Thank you very much. Thanks for the nice presentation. Are there any questions from the audience?
Very general questions.
Just one comment, the commutator and anti-commutator, I've never seen this notation.
Yeah, I agree, because I like our notation more because the origin curly bracket and the square bracket is very
Yes.
strange, because if you talk about set, it's confused. Yeah, that's my.
Yeah, that's true. But yeah. Okay, so if there are no questions, then thanks again for the nice presentation.